think I was at a PD session once, and they said that your background should be like, blue and calming and stuff. And so I think I made this, and it really made no difference to the class, so I stopped doing it. But I've never changed the background. Am I recording here? What is going on? Okay, whatever. Work and power. Won't take long at all to do. It will at this rate, though. So what is power? It refers to the rate of doing work. Right now, we are not very powerful. We are not being very speedy at our doing work. And again, we're talking about the scientific sense of the word work, right? You could also say that it's the rate at which energy is transferred from one object to another. So when I push the computer cart across the room, down the hall or whatever, I'm transferring energy to it. I'm burning up Fruit Loops energy and converting it into kinetic energy. And there's probably some friction involved, and so there'd be some heat energy as well. So it's how fast that energy is transferred. When you burn gasoline in your car, it's how fast the gasoline is used and the kinetic energy that is then produced. Okay? So we know that it refers to the amount of work done per unit of time. So mathematically, it's simply power is equal to work divided by time. It really is not very hard at all. And I actually think, now that I know a little bit about grade 9 science, that it was introduced to you in grade 9 science when you talked about electricity. And you may have talked about kilowatt hours and stuff. Anybody remember that at all? No? Maybe your teacher did a lousy job? Okay. Can't believe that. With Mr. Friesen? Mr. Friesen. If it's in the curriculum, Mr. Friesen covered it. That I know. Okay. So what are the units of power? Well, work is measured in joules. Time, of course, is measured in seconds. So technically, the unit of work, the unit of power is the joule per second. But because that's not that clumsy, but because they wanted to give Mr. Watt a little bit of attention, some recognition that he deserved, 1 joule per second is defined as 1 watt. And I think I have a picture of him. No, I don't. James Watt, the inventor, not the inventor, the guy that took the steam engine and actually made it practical. Often referred to as the inventor of the steam engine, but not true. One of those trivia controversies. Okay, so when we talk about watts, when you talk about a 75 watt light bulb in your home or a 100 watt light bulb, same idea, right? That's what a watt is. Talk about like a 200 watt microwave or something like that. Again, same unit there. Now, if you've got a 200 watt microwave and someone else has a 600 watt microwave, well, it means that it's just going to heat up your leftover pizza a little bit quicker, that's all. So here's a very quick sample question because they're really not very hard at all. What power does a 50 kilogram girl develop while running up a 2 meter high flight of stairs in 0.75 seconds? Golly, I wonder when you could use this type of information. Tomorrow morning. Right? So you're going to take your mass.
Yeah.
You're all going to jump on here. Now, conveniently, I've already converted it to newtons for you, but it's by stepping on here you get it in newtons, right? Oh, I seem to have gained a newton or two over the weekend. That's not good. Yes, you're going to have to measure the height of the stairs, right? What we normally do is there's 2 sort of flights. We usually just do the bottom one because are you technically doing work? You climb that first flight of stairs and you take 2 or 3 steps and you go horizontally. Are you doing work during that time?
Yes.
No, because you're not raising your potential energy, right? So you're not technically doing work, and so it's kind of wasted time. So we usually just do the that bottom 12 or 13 stairs.
So does work count on a horizontal point? Some of the questions made it sound like it did.
Really? You can do work horizontally. This just has to be the force, and the distance has to both be in the same direction, right? But when you simply walk across, like when I walk across the room like this, is my gravitational potential energy any different over here? Did I increase my energy anyhow? No. So I really don't do any work. Right? Yes, I know.
So,
To do work, you just have to increase your potential energy.
That's what I'm getting.
I mean, I guess, okay, I guess there is a small amount of work done. My kinetic energy right now is 0. My kinetic energy right now is greater than 0, right? But once I get up to speed, I don't need to apply any more force. I only need to accelerate myself. So just in that very brief sort of instant where I'm actually pushing, right, there's actual force involved, I guess I'm doing a small amount of work right there, right? But once I'm up to speed, technically I don't have to apply any more force. Except that, there's obviously air resistance, right? I'll get to you. If you're walking through a swimming pool and there's considerable friction, right? Do you do more work? Like if you walk from one end of the pool to the other end of the pool? Yeah, that's work, right? I mean, and you burn energy, there's no doubt about that. It turns into heat. But you are applying a force in the direction, so yeah, you're doing work. Just that we're talking minimal air resistance. I know that just further cloudies the issue, doesn't it? Right. Jason.
So does walking downstairs do negative?
Guess it would have to, wouldn't it? Where does that energy come from? Gravity, I guess. Yeah, I don't know. Man, you guys are full of tough questions. Let's just make pancakes, you guys. No, she does work against the pull of gravity. So we're just going to talk wait force here.
How do we see how much heat energy the griddle makes to cook the pancakes on that thought?
We could actually, we could rate it'll have a rating on there. Oh, there's all sorts of things we can do. I'll bring the pancakes if someone wants to bring the syrup. Is that a deal? I like the Saskatoon syrup, it's nice. I'll bring the pancake next. Product is work over time, so in this case here, it's weight force times the distance divided by the time. MGD, mass times gravity times distance. So 50 times 9.8 times 2 divided by 0.75. How come it's 0.75? Is that the time? Okay, that seems like an awful short amount of time. 2 meters, yeah, I guess. 1,306.7 watts or 1.31 kilowatts. We have found during the personal power lab that people's personal power could be anywhere from about 600 watts to up over 1,000 in that 1,300 watt range. That's pretty extreme. It's generally some of the larger gentlemen in the room that develop that kind of power. Anyone that's sort of larger and has any sort of athletic ability and can run upstairs real well is going to have a personal power rating pretty high. 1 horsepower is about 750 watts. I don't think there's anyone that would think they're more powerful than a horse. So I'm really not sure why we don't get values that are, like you would think, okay, I'm probably about, maybe a quarter horse kind of thing. So I really don't know why we get such large values. Pardon me? 1 horse is about I think it's 745 or something like that. It's in here. It's in there. 750?
I think it's approximately 750, yeah.
Okay, so yeah, no 1 kilowatt, of course, is 1,000 watts. The textbook, I want to show you this because I will assign some textbook questions. The textbook uses a slightly different formula, kind of a neat little formula derivation kind of thing, because V equals D over T, power equals work over time, which is F times D over T. Use your vast experience with formula derivation and tell me what the formula is. Come on. You can do it. Yep. P is equal to FV. You don't see that one very often, but the textbook does have questions that use that. So
questions they give you a velocity.
Yeah. You can figure out. Yep.
Oh.
Yep. That's all. I mean, you could work sort of backwards and come up with this kind of thing too, but kind of a handy little thing. So there's some textbook questions. There's not a lot. I just throw them out there as additional sort of practice ones for you. I'm going to give you some more as well. I think you've got a couple of work handouts, right? And they have power questions sort of interspersed, and I've said ignore them for now. Maybe you've been doing them already. Hopefully this will help. I don't know why that's there. Super Grover. Someone was on a Super Grover kick one year. Maybe put that in there. Maybe it's because, I don't know. I don't really remember. It's been so long. 2005? Oh, you mean it's been so long since I can't? No.
Since you made it.
Oh, I probably made that about, I don't know, 6 or 7 years ago. That's that little slideshow.
Oh, it's like
Making them better and better every time. Let's read the handout and then we'll do the quiz. So the quantity work has to do with the force causing displacement. Work has nothing to do with the amount of time that this force acts to cause the displacement. Sometimes the work is done very quickly, and other times the work is done rather slowly. For example, a rock climber takes an abnormally long time to elevate her body up a few meters along the side of a cliff. On the other hand, a trail hiker who selects the easier path up the mountain might elevate her body a few meters in a short amount of time. The two people might do the same amount of work, yet the hiker does the work in considerably less time than the rock climber. The quantity which has to do with the rate at which a certain amount of work is done is known as power. The hiker has a greater power rating than the rock climber. Power is the rate at which work is done. It's the work-to-time ratio. Mathematically, we've already seen the formula. The standard unit of power is the watt, as implied by the equation for power. A unit of power is equivalent to a unit of work divided by a unit of time. Thus, a watt is equivalent to a joule per second. For historical reasons, a horsepower is occasionally used to describe the power delivered by the machine. 1 horsepower is equivalent to approximately 750 watts. And if you want to do a little Google search on the original definition of a horsepower, it had something to do with how much water a horse could haul out of a well in a 30-minute period or something like that. I don't know. So it really depended on actually how powerful the horse was. It was kind of like the definition of a foot, right? You know, it was the king's foot kind of thing. Well, people have different size of feet, and so it really wasn't very good as a scientific unit. Most machines are designed and built to do work on objects. All machines are typically described by a power rating. A power rating indicates the rate at which that machine can do work upon other objects. Thus, the power of a machine is the work-to-time ratio for that particular machine. A car engine is an example of a machine which is given a power rating. The power rating relates to how rapidly the car can accelerate the car. Suppose that a 40 horsepower engine could accelerate the car from 0 miles per hour to 60 in 16 seconds. If this were the case, then a car with 4 times the horsepower could do the same amount of work in 1/4 the time. That is, a 160 horsepower engine could accelerate at the same time from 0 to 60, in other words, the same mass, in 4 seconds. The point is that for the same amount of work, power and time are inversely proportional. Equations can be guides for thinking about the relationship between quantities. The power equation suggests that a more powerful engine can do the same amount of work in less time. A person is also a machine which has a power rating. Some people are more powerful than others. That is, they are capable of doing the same amount of work in less time or more work in the same amount of time. In the personal power lab, which you're doing tomorrow, students determine their own personal power by doing work on their bodies to elevate it up a flight of stairs. By measuring the force, displacement, and time, we were able to measure our personal power rating. Suppose that Ben Pumping Iron elevates his 80-kilogram body up a 2-meter stairwell in 1.8 seconds. If this were the case, then we can calculate Ben's power rating. It can be assumed that Ben must apply an 800 Newton downward force because he weighs 80 kilograms. They took 80 times 10 instead of 9.8, just for rough guessing. 800 Newton downward force upon the stairs to elevate his body. By doing so, the stairs would push upward on Ben's body, and yet just enough force to lift his body up the stairs. It can also be assumed that the angle between the force of the stairs on Ben and Ben's displacement is 0 degrees. In other words, he sort of elevates himself straight up and then sort of goes forward. So we are sort of fudging the numbers a little bit here. With these two approximations, Ben's power rating could be determined as shown. So 800 newtons, mass times gravity, times 2 meters, divided by 1.8 seconds, 889 watts. Ben is 889 watts by a horse. Right now. The expression for power is work divided by time. Now, since the expression for work is force times displacement, the expression for power can be rewritten as blah, blah, blah. There it is again. Force times velocity. Okay. Let's jump in and do the question. Go get yourself a quick. Let's see how you did. Question number 1, everyone? Everyone got question number 1 right. So I won't need to go through that. Which student delivers the most power? It is Ben. Why is it Ben? Doesn't he do it quicker or something or other? 10 seconds? Yeah, 1 minute, right? So Ben does it much quicker, so he is more powerful. During a physics student, Jack and Jill ran up the hill. Oh, it's even here. Jack is twice as massive as Jill, yet Jill ascends the same distance in half the time. Who did the most work? Why is it Jack? They ran up the hill. Jack is twice as massive, which means he needs 2 times as much force, right? And Jill ascends the same distance in half the time. But the question is, who did the most work? Does the time have anything to do with the amount of work? Nothing to do with it. I threw you a curveball. Okay? Jack does more work because he has to apply twice as much force. The time makes no difference at all. Correct answer is A, Jack. Who delivered the most power? That is the same. He does twice as much work, but she does it in half the time. So they do this, have the same amount of power. Tired squirrel, mass of approximately 1 kilogram. That's a big squirrel, 2.2 pounds. Does push-ups by, who's seen, I don't know, squirrels doing push-ups. If the tired squirrel does all its work in 2 seconds, determine its power. So it's work divided by time, right? So it's simply going to be 0.5 divided by 2, 0.25 watts. Oh. Fair enough, yeah. But, okay, because they give you the work, that's what you use, yeah. Now I understand your question. I didn't understand it before, Jason. Yeah, I got you. No worries. When doing a chin-up, a physics student lifts her 42 kilogram body distance of 0.25 meters in 2 seconds. What is the power delivered by the student's bicep? 51.5 is the answer. 1 decimal place. How many people got that?
I put 51.4.
Oh. Jason, what did you say about 10, 15 minutes ago to Corey? I really should have read more of that question. I heard you say that. I know. Just saying. Read the question. Sounds like you guys got it. It was just the punching in the answer that didn't do so well, right? So it's going to... I suppose you just truncated instead? Principle's the same. I'll leave it at that. Okay, I'm guessing that number 7 was a little bit of a challenge. I got 3, what is that big number? 9 of you got it right. So 1 kilowatt hour, right, is a flow of 1 kilowatt of electricity for 1 hour. Use conversion factor to show how many joules of energy you get when you buy 1 kilowatt hour of electricity. So 1 kilowatt is 1,000 watts for an entire hour. Where does 3,600 come from? 60 seconds in a minute, 60 minutes in an hour. So it's 3,600,000 joules. That's a lot of Fruit Loops. Escalators used to move 20 passengers every minute from the first floor of a department store to the second. The second floor is located 5.2 meters above the first. The average passenger's mass is 54.9. Determine the power requirement. Round to the nearest whole number. So our total mass is going to be 20 times 54.9, and I'll have to get a calculator. Given enough time, I probably could come up with the brain power to do it. (1098). Weight force is mass times gravity. 1098 multiplied by 9.8. 10760.4. And we want to know power, right? Work over time, so that's going to be F times D over T, 1076.4. The distance is 5.2, and it has to happen in 1 minute, 60 seconds. So that big number times 5.2 divided by 60, 932 point total number. I guess that would be 933, right? 933 watts. Yes. Is 933 watts a lot? Doesn't seem like very much, does it? Okay, that's a little over 1 horse. I think you would need more than 1 horse, considerably more than 1 horse, to drag 20 people up a flight of stairs. So I'm not sure that that is probably very accurate. But I guess it's in 1 minute, so we're talking pretty slow, aren't we? Really, right? 1 minute's a long time, yeah. Okay, fair enough. Everything's got a power rating on it. If you go back there and look at that fan that I had brought in September when it was really hot, it will have a power rating on it. What does that mean? Like if I've got a more powerful fan, what does that mean? Yeah, but in the real sense, like what does it mean when you're buying fans? It's going to blow more, it's going to blow the air faster, right? It's going to blow the air faster, exactly. Okay, I will stop. You've got lots of a variety of questions. If you need more power questions, remember there's the textbook ones as well. We only got about 10 minutes left. If you could get yourself figured out groups tomorrow, you'll need, everyone has to run upstairs, and then you determine everyone's power rating, and then there's a few questions in here as well. If you want, you can actually begin some of the questions. There are 2, you have to hand in the sheet of paper as well, showing me your work, but it should be on the video as well. So you have to do all that. When you get to the second page, it says post-doc questions. Questions 1 to 5 on the second page are pretty easy. You have to do them all, but I want 1 on the video. Just 1 on the video, but you have to do them all. Okay? And then on the back side, questions 6 and 7 are particularly challenging. Okay? You only have to have 1 of those done on the video, and you only actually have to do 1. Okay? You'll notice that there's some vector cereal there as well. Vector with milk, 285 calories is 1,190 kilojoules. Okay, and on the right hand side you've got Raisin Bran. Notice that they only list it in calories, so you have to do some ratio proportion to figure out what the joule equivalent of 180 calories is for Raisin Bran. Okay, so I'll leave you alone. That's the plan for the next couple days.
Did you give us a calorie?
No, you're going to have to figure it out from the vector one. It's right there.